So now let's go over our practice exercises for calculating concentration. So we start out here relatively simple. We're looking for the molarity of a solution given a certain amount of solute that's dissolved. The most challenging thing here that you need to remember is what is the actual chemical formula of sodium nitrate? So by this point we should be pretty comfortable knowing our polyatomic ions. And we know that sodium nitrate is NaNO3, which has a molar mass of approximately 85 grams per mole. So we can use that to calculate the number of moles of sodium nitrate. We have 27.3 grams of it. Divide by the molar mass. And we get that we have 0.321 moles. From there, in order to figure out the molarity, we just need to take that number of moles and divide by the volume in liters, and we get 0.11 molar. All right, for number 2, we're looking now for molality. Remember that the key difference between molarity and molality is in the denominator. Molarity uses liters of solution. Molality uses kilograms of solvent. So the kilograms of solvent is the easy part here. We have 100 milliliters of water. Knowing that the density of water is 1 gram per milliliter, that's 100 grams, or 0.1 kilograms. For the sodium bromide, the solute, we're going to again have to calculate the number of moles. So we take the grams of sodium bromide and convert to moles using the molar mass. 1 mole of sodium bromide is 103 grams. Gives us 0.228 moles. And so now we take this number and we plug it into our molality equation. And we find that this solution is 2.28 molal. All right, in question 3, previously we were dealing with molarity and molality. Here's an example of percent. So we know that our percentage is equal to 100 times the amount of the solute, which is the glucose, but that we don't know. That's what we're asking for in the question. So we'll call that X over the amount of the solvent. Now notice in this case, this is a weight per volume. So it doesn't matter that these are 2 different units. In fact, they have to be 2 different units. And so solving for X here, we find that we have 37.5 grams of glucose. All right, the next couple questions, we're going to go back to molarity. Again, that's the one we use most often. But here I'm not asking you to calculate the molarity. The molarity is already given to you. And what I want to know here is the amount of the solute that we need. So we know the volume of the solution, that's also given. But I'm asking how many grams of the solute. So the moles of solute are an unknown. But if you think about what moles mean and how we find moles, once we know the number of moles, we can use the molecular weight to convert that back to grams. So we find here that X is equal to 0.38 moles. Now we can take that number of moles and multiply by the mass of our solute. Our solute here has a mass of 82 grams per 1 mole. And so we find out that to make the solution as desired, we would need 31 grams of solute. So now we're dealing with the third thing that we could try and calculate from a molarity question. Now we know the amount of the solute, we know the concentration. What we want to find is the volume. So we can say that 0.15 molar, that's our concentration, is equal to some number of liters and some number of moles. But before we can get moles, or before we can plug that in, we're going to have to calculate that, because the amount of solute, the HCl, is given here in grams. So we use that to calculate the number of moles, and then we plug that in. From here, it's just a matter of solving for x, and so we get x is equal to 0.73 liters. Now our next question is another molarity question. This one deals with the concentration of glucose in blood. So one of these units we didn't talk a whole lot about before, but it's another metric prefix, is the prefix deci, D-E-C-I. And deci is essentially 1/10 of the original amount. So 10 deciliters make up 1 liter. And while it's a unit we don't use very often, interestingly, when we measure things like sugar concentration in blood, that often gets expressed in deciliters. I don't know why that unit still gets used, but we still see it there. But what we find here is that the normal concentration of glucose is 100 milligrams per deciliter. Or, to put it in more useful units, this would be 0.1 grams in every 0.1 liters. Well, if you think about it, there's a way to make that one easier to work with. Because if there's 0.1 grams in 0.1 liters, how many grams would be in 1 liter? 10 times that, because it would be 10 times the volume. So we can say that normal glucose concentration is 1 gram in 1 liter. Now, we don't have to do that step. We can go through and calculate the moles using the 0.1 grams and the 0.1 liters. It's just that, in my opinion, this one extra step makes our future steps, our additional math steps, a lot easier. So we can now say 1 gram of glucose and convert that to moles. So the chemical formula of glucose we can look up. We find it's C6H12O6. that has a mass of 180 grams. So we have a very, very small number of moles here, 0.00556 moles. But then all we need to do is take that number of moles that we've calculated and divide it by the 1 liter. And we get 0.00556 molar. And so maybe that's why we use milligrams per deciliter for blood concentration, because 100 is a much easier number to remember than 0.0056 or 556. All right, question 7. We now have a situation where we're given a concentration. And I want to know what the percentage is. And this experiment is one that you can actually fairly easily do in the lab. In fact, in past years, we've actually done this as an experiment, where you take actual samples of vinegar and you do a titration. A titration being an experiment where you use, for example, if we're trying to figure out the concentration of the acid, we would use a solution of base that we've determined its exact concentration of and use that to determine the concentration of an acid. But we find that the molarity of acetic acid in vinegar, acetic acid, if you're not familiar with it, when you open a bottle of vinegar, the smell that you immediately get from that bottle, that's acetic acid. So we find the concentration to be 0.883 molar. And we want to know what the percent of acetic acid is. So the biggest challenge here is that we haven't defined a volume. But it turns out it doesn't matter. This could literally be any volume. It could be 100 milliliters, it could be 1 liter, it could be 100 liters. And so in a situation like that, I'm going to choose the easiest amount to work with. So I'm going to assume 1 liter. And then given that the concentration is 0.883 molar, I know then that in that 1 liter has to be 0.883 moles. Well, if I'm looking now for percent weight per volume, I'm going to convert that volume to milliliters. But then I need to convert my mass, 0.883 moles, into a mass. Acetic acid has a molar mass of 60 grams per 1 mole. And we get that there's 53 grams of acetic acid in a liter of vinegar. So I can put that here now, multiply by 100, and I get that the acetic acid is 5.3%, or the vinegar is 5.3% acetic acid. Now, it might be one of those things that you've never noticed, but the next time you're using vinegar, take a look at the bottle. And what do you see on that bottle? Well, look very carefully down at the bottom, and somewhere it'll tell you it's about 5% acidity. All right, 2 problems to go here. The next one is a dilution problem. We have 12 molar HCl, and that's actually the way hydrochloric acid is sold. If you ever use it in that concentration, you want to be very, very careful. It's pretty nasty stuff. And I mean to the point of if you accidentally inhale some of it, which I've done before, not intentionally, but it happens. Safe to say it'll clear out the sinuses very, very effectively. But we want to use that to prepare a 2 molar solution. So if you recall, we use our M1V1 equals M2V2. So our initial molarity is 12 molar. Our V1, the amount of it we need is unknown. We want to make a 2 molar solution, and we want 500 milliliters of that. So we solve for V1 here. V1 here is 83 milliliters. So what this means, if we want to make 500 milliliters of a 2 molar HCl solution, we need 83 milliliters of 12 molar solution, and then we add water until we get to 500 milliliters. All right, our final question on this practice, on these practice exercises, is to calculate parts per billion. And what I've given you here is the amount of vitamin B6 in a serving of orange juice. And so I want you to convert that to parts per billion. So parts per billion is the amount of solute over the amount of the solvent times 10 to the 9th. So the amount of the solute is the vitamin B6. That's 0.130 milligrams. But we need the amount of the solvent, or of the juice, in milligrams also. So we can take our 240 milliliters and convert that to grams, because we said assume the density is 1 gram per 1 milliliter. That'll give us grams, and then we need to go to milligrams. 1,000 milligrams over 1 gram is equal to 240,000 milligrams. We multiply that result by 10 to the 9th, and we find that the concentration of vitamin B6 in orange juice, when expressed as parts per billion, is 542 parts per billion.